Welcome to Chapter 6. This is your Professor Atif Reed Muhammad. Let's look into together on recovering data in a little bit more depth. We'll explain the techniques for hiding and scrambling information as well as how the data is recovered. The key concepts discussed in this lecture are undeleting data in Windows, Linux, and Mac operating system, recovering information from the damaged drives, undeleting data. Simply deleting a file will not keep authorities from discovering it. Expect the evidence will frequently be deleted from computers you examine. File systems and hard drives. Clusters and sectors. Operating systems views clusters which are one or more sectors. File system views clusters which are one or more sectors, and hard drives divided into sectors of 512 bytes or 4096 bytes. Windows has FAT16 and FAT32 used in pre-Windows 2000 versions. NTFS or anti-file systems, it's technically new technologies of networking technologies. File system is in use since Windows 2000. Uses a table to map files to specific clusters where they are stored on the disk. FAT is storing a file in Windows. Record cluster number for next cluster. Add EOC if at end of chain. Mark bad reserved open clusters. Deleting a file in Windows. When a file is deleted, data is not removed from the disk. FAT is updated to reflect clusters no longer in use. New data saved to those clusters may overwrite old information. Master file table is MFT. Describes all files on the volume including file names, timestamps, and so on. Serves the same purpose as the file allocation table in FAT. That is also the file allocation table, or FAT32 and FAT32. Cluster bitmap, a map of all clusters on the hard drives. I would suggest you to read these details in your prescribed text. Deleting a file in Windows. When a file is deleted, data is not removed from disk. Clusters are marked as deleted and moved to recycle bin. When recycle bin is empty, clusters are marked as fully available. File name in the MFT is marked with a special character that means the file has been deleted. Disk digger, free and commercial versions. Free versions recover one file at a time. Here is a disk digger, how it looks like. Starting the data recovery, you can see the NTFS partition no label, and then you press next when you dig deep. Recovering an individual file using disk digger. When undelete, easy to use, wizard driven. When undelete wizard, step 1, selecting a drive, and that's how it looks like. When undelete wizard, step 2, selecting the file types, looks like this. Wizard step 3, selecting a restore file location, looks like this. Free undelete, free tool for personal use, commercial versions available as well. Free undelete, selecting a drive, you'll have to go through these steps. OS Forensics, a robust forensics tool that also provides the undelete from the unmounted image or from a live system, the operating systems forensics. That looks like this. And you carry on looking at the results like this. Autopsy, free open source digital forensics tool included includes deleted file recovery. When a disk image is loaded, it immediately begins recovering deleted files. Important because evidence is often found in deleted files. It looks like this. Linux has file system extension 3, extension 4. Storing a file in Linux stores file in contiguous blocks. Blocks sometimes need to be extended. Exact size of blocks depends on parameters used with the command that create the partition. Uses inodes and soft links. Recovering a file in Linux, move system to single user mode with init 1 command. Use grep to search and recover files. Example is given like this. Scalper works with Linux and Mac OS. Possible to compile source code to work in Windows. You install, verify the output directory is empty, edit config file or configuration file, run scalpel command. Mac OS X and later versions are based on FreeBSD, a Unix clone much like Linux. Mac OS currently uses Apple File System or APFS and HFS Plus or Hierarchical File System Plus. Mac Keeper recovers deleted files on Apple computers. Free, fully functional trial version available. That's how it looks like. The file recovery tool, it actually gives us the chance to undelete from the hard drives. Recovering information from damaged media. Remove drive connect to test system, boot test system, copy files from drive to test file, remove drive connect to test system, and that can go up to image drive content. Let's look into this with an example. In the realm of digital forensics, recovering information from damaged media is a critical task that often presents significant challenges. This process involves extracting data from storage devices that have been compromised due to physical damage, software corruption, or intentional tampering. Forensics analysts employ a variety of techniques and specialized tools to salvage valuable information, which can be pivotal in legal investigations, data recovery, and ensuring business continuity. Consider a case of a prominent bank that recently suffered severe data loss due to the fire in their data center. The bank's IT department was unable to retrieve crucial financial records from the damaged hard drives, prompting them to engage the services of forensic analyst Mr. Brown. Mr. Brown's first step was to assess the extent of the damage. He carefully examined the hard drive, noting any visible physical damage and using diagnostic tools to evaluate the drive's internal components. This initial assessment helped him determine the most effective approach for data recovery. Mr. Brown began the recovery process by creating a forensic image of the damaged hard drive. This step is crucial as it ensures that the original evidence remains unaltered, preserving its integrity for legal purposes. Using specialized software, he created a bit-by-bit copy of the drive, including all sectors, even those marked as bad or unallocated. This forensic image served as a safe working copy, permitting Mr. Brown to attempt various recovery techniques without risking further damage to the original drive. Next, Mr. Brown employed advanced data recovery tools to scan the forensic image of recoverable data. These tools are designed to identify and reconstruct file fragments even from severely damaged or corrupted media. In the bank's case, Mr. Brown focused on retrieving critical financial records such as transaction logs and customer account information. He used file carving techniques to extract data based on known file structures and signatures, uh, piecing together fragments to reconstruct complete files. After successfully recovering a significant portion of the lost data, Mr. Brown meticulously documented his findings and the methods used. The documentation is essential for maintaining a chain of custody and ensuring the admissibility of the recovered evidence in the court. He then presented the report to the bank detailing the extent of data recovery and providing recommendations for improving their data backup and disaster recovery strategies. Mr. Brown's expertise and diligence not only helped the bank retrieve vital information but also highlighted the importance of proactive measures to prevent such incidents in the future. Replace printed circuit board, replace write and read head assembly, transfer disk platters to healthy drive, and that allows us also to continue extracting the information. Recovering data after the logical damage. Now let's look into that in a detailed example. So let's take another example of an e-commerce retail store or e-commerce store. Data integrity and availability are paramount for e-commerce. However, the logical damage such as accidental deletion, software bugs, or malware attacks can lead to significant data loss, impacting both the business and its customers. Recovering the data after logical damage involves a different set of challenges and techniques compared to physical damage, focusing more on software-based solutions and forensic analysis. Imagine an e-commerce store that experienced a catastrophic data loss due to the software glitch which corrupted their product database and deleted thousands of customers' orders. The store's IT team attempted to restore the data from backups but found that most recent backups was also corrupted. Desperate to recover the lost data, they turned to forensic analyst Mr. Brown. As we discussed earlier, for assistance, Mr. Brown's first task was to understand the nature of logical damage and identify potential recovery vectors. Mr. Brown began analyzing the e-commerce platform's database and file system, looking for any remnants of the deleted data. He used specialized data recovery software designed to scan and recover data from logically damaged media. These tools can often find and reconstruct deleted and corrupted files by examining the raw data on the storage device. In this case, Mr. Brown focused on recovering the lost product information and customer orders, which were crucial for the store's operation and customer satisfaction. During his investigation, Mr. Brown discovered that the e-commerce platform used a SQL database to manage its data. He employed advanced database forensics techniques to analyze the transaction logs and data journals, which often contain remnants of deleted or modified data. By carefully parsing through logs, Mr. Brown was able to extract valuable information about the lost orders and products. He then used this information to manually reconstruct the deleted records, cross-referencing the data sources to ensure accuracy. After the arduous recovery process, Mr. Brown successfully retrieved a substantial amount of the lost data. He documented his findings, methods, and tools used in a comprehensive report which he presented to the e-commerce store's management. In his report, Mr. Brown emphasized the importance of maintaining robust and frequent backup strategies as well as implementing database replication and redundancy measures to prevent future data loss. Additionally, he recommended regular software audits and updates to minimize the risk of logical damage. By following these recommendations, the e-commerce store could enhance its data protection, measures, and better safeguard its critical information. So, recovering data after logical damage, Microsoft Windows is check disk, Linux is FSCK, Mac OS is disk utility, and the sleuth kit and test kit. Preventing logical damage. Let's look into this with an example. Let us look at a scenario where one of the character I'm going to discuss is, changing the name, it's David, stood before an assembled staff of a data center, ready to deliver a critical training session on preventing logical damage. He knew that while physical security and hardware maintenance were crucial, logical damage could be just as devastating and often went overlooked. Today, David aimed to change that perception and equip the staff with the knowledge they needed to protect the data center's digital assets. Imagine this, David began the training like that. One of our system administrators, let's call him Alex, receives a phishing email disguised as an urgent request from a superior. The email contains a malicious attachment that, when opened, infects Alex's workstation with ransomware. Within minutes, the ransomware encrypts not just Alex's local files but also spreads the network shares he's connected to, causing logical damage to our critical data. David paused here to let the scenario sink in with the staff. Now he starts again. Now, how could Alex have prevented this? David asked this question to the audience. First, always be cautious of emails from unknown or unexpected senders. Look for signs of phishing, such as suspicious email addresses, generic greetings, or urgent language. Never open attachment or click on links unless you are absolutely sure that they are safe. David continued, second, regular software updates and patches are essential. Outdated software is a common entry point for malware. Ensure that your operating system, antivirus software, and other applications are also up to date. This not only protects against known vulnerabilities but also helps maintain overall system stability. David then emphasized the importance of access controls and permissions. Alex shouldn't have had unrestricted access to critical network shares, he explained. Implement the principle of least privilege. This means giving users the minimum level of access they need to perform their jobs. This limits the potential damage if a user's account is compromised. In conclusion, David stressed to the staff the need of robust backup strategies. Regular backups are our last line of defense against logical damage, David said. Follow the 3-2-1 backup rule. Keep at least 3 copies of your data on 2 different storage devices with a 1 copy off-site. Regularly test your backups to ensure that they are working correctly. Remember, it is not just about creating backups, it is about being able to restore them while needed. David ended the training session with a question and answer, encouraging the staff to ask questions and share their own experiences. By doing so, he fostered a culture of learning and vigilance, ensuring that everyone understood their role in preventing logical damage and maintaining the data center's security and integrity. Hopefully, this had been helpful. Consistency checking. That's also an important aspect. Involves scanning our disk's logical structure to ensure that it is consistent with its specification. Verifies that a dot entry points to itself and a dot dot entry points to its parent. Checkers include check disk and FSCK can fail if the system is highly damaged. CHK disk or check disk might delete files that are out of place or unexplainable. Install the operating system on the separate partition from the user's data. Zero knowledge analysis. This is very important. Let me share with you a real use case. I will be changing the places and the names of the organizations in this. Let's say there was a metropolis of megacity, the Transport Authority was faced with a daunting challenge: how to optimize route planning and improve service efficiency without compromising the privacy of millions of commuters. The traditional approach of analyzing passenger data directly was a non starter due to the stringent privacy regulations and public concerns about surveillance. Enter the innovative solutions of zero knowledge analysis, a cryptographic technique that allows data to be studied without revealing the underlying information. Imagine the Megacity Transport System, or MTS, wanting to understand commuter patterns to better allocate resources and reduce overcrowding. Traditionally, they would collect and analyze vast amounts of data, including individual travel histories, to identify trends and hotspots. However, this approach raises significant privacy concerns. Zero knowledge analysis offered a way to gain insights without ever seeing the raw data. Here's how it worked. The MTS partnered with a tech firm specializing in zero knowledge proofs. Instead of collecting raw data, the tech firm deployed a system that allowed commuters to submit encrypted versions of their travel records. These encrypted records were then aggregated and analyzed using advanced cryptographic techniques. The analysis could reveal patterns such as peak travel times and popular routes without ever decrypting the individual records. For example, the system could determine that a particular bus route was heavily used between 7 a.m. to 9 a.m. without knowing who the commuters were or their specific travel histories. This information was invaluable for MTS, enabling them to adjust bus schedules and more vehicles during peak hours, and even plan new routes based on demand. All this was achieved without compromising the privacy of individual commuters. The implementation of zero knowledge analysis not only improved the efficiency of the megacity's transport system but also built trust with the public. Commuters appreciated the commitment of the privacy, knowing that their travel habits were being used to enhance services without invading their personal space. This case study highlights the power of zero knowledge proofs in balancing the needs for data driven decision making with the imperative of protecting individual privacy. As cities around the world grapple with similar challenges, the lesson from Megacity offers a promising path. And that's how it is used in the practical world. So let's take another example for zero knowledge analysis and in more depth understanding how it helps the computer forensics area. So there is let's take an example of an aviation industry, and you might have known the CrowdStrike issue that happened lately in the year 2024. So ensuring the robust disaster recovery mechanisms is paramount for airline and aviation industry as well, along with all the areas. When a major airline, let's say take a name Skyflight, experienced a severe data breach that compromised its flight scheduling and passenger manifest system, the company needed to swiftly restore operations without exposing sensitive passenger information to further risk. This is where zero knowledge analysis comes into play, offering a means to analyze and recover data without revealing an underlying sensitive information. Imagine the chaos at Skyflight when the cyber attack corrupted their central database, disrupting flight schedules and passenger records. Traditional disaster recovery methods would involve assessing and analyzing raw data to identify the extent of damage and restore the system. However, this approach posed significant privacy risks as it would require handling sensitive passenger information, including personal detail and travel itineraries. To address this challenge, Skyflight partnered with specialized firm that employed zero knowledge analysis techniques. Instead of assessing the raw data directly, the tech firm implemented a system where encrypted versions of flight schedules and passengers' manifests were submitted. These encrypted records were then aggregated and analyzed using advanced cryptographic methods. The analysis could identify patterns of corruption and pinpoint the affected areas without ever decrypting the individual records. For example, the system could determine that flight schedules for a specific route were corrupted without revealing the detail of individual flights or passenger information. This allowed Skyflight to focus its recovery efforts on most critical areas, restoring flight schedules and ensuring that passengers were notified of any changes without compromising their privacy. The implementation of zero knowledge analysis not only accelerated Skyflight's disaster recovery process but also maintained the trust of its passengers by ensuring that sensitive information remained encrypted and inaccessible during the analysis. Skyflight demonstrated its commitment to data privacy and security. This approach also mitigated the risk of further data breach during the recovery phase, as the analysis was conducted without exposing the raw data to additional vulnerabilities. Moreover, this case study highlights the broader applicability of zero knowledge proofs in disaster recovery scenarios. By leveraging these cryptographic techniques, organizations can swiftly and securely restore their systems without compromising the privacy of their users. As the threat landscape continues to evolve, adopting zero knowledge analysis in disaster recovery plans can provide a critical layer of protection, ensuring that sensitive data remains secure even in the face of significant disruptions. In this lecture, we have looked at undeleting data in Windows, Linux, and Mac OS, recovering information from damaged drives. I hope to see you in next lecture, and happy learning.